Hello everyone, I want to introduce the speaker for this slot. The man you're about to hear from is the technical mind behind kernel and virtual machine development at Microsoft right now. I was interning there this summer, and one of the things I got to do was hear him speak a lot. And I kept going back because I find him a very exciting speaker. He's got a lot of crazy ideas, and I like them all. So welcome Eric Traut, please.
All right, thank you, Tak. So as Tak mentioned, I have the privilege of running a team at Microsoft. It consists of about 200 very bright engineers. We're responsible for the core kernel of Windows, which constitutes the traditional aspects of a kernel, everything from scheduling to memory management, as well as power management, the boot sequence, and I'm also responsible for our virtualization technologies. And some of you might be familiar with the products that we have in the market today, Virtual PC and Virtual Server. I had a hand in writing major portions of those products. And we're also working on a new technology that's going to become part of the Windows platform in the very near future. We've been working on this for the past several years. And so I figured I'd come and tell you a little bit about some of the architectural decisions that we made as we were putting that platform together. It's been a lot of fun for me to work on this, and so it's fun to talk about it. I'll leave some time at the end, and if we have some time, I'll show a few kind of fun little demos at the end as well. I also want to talk a little bit about some of the things that are driving virtualization today. I think most of you are probably familiar with the fact that virtualization is really big. You see it a lot in the news, and there are good reasons why it's being deployed by people around the world. Some of the reasons, though, are kind of interesting. It's being used to solve some problems that admittedly exist today in the operating system, especially in Windows. You're going to hear me be somewhat self-deprecating here today. I'm going to fully admit that there are some major problems in the Windows OS that are driving some of these things, and virtualization is one way that we can tackle them, but I'm going to also talk about some of the other things that we're doing to tackle them kind of at the root of the problem. So with that, let me jump in. Let me first of all kind of back way up before I jump into what virtual machines are. I think most of you have used virtual machines. I used to start off my talks by asking people how many had used virtual machines. And 3 years ago, I'd get maybe a quarter of the people in the room raising their hand. I don't even bother anymore because everyone's heard of virtual machines. Everyone uses them. So, but the whole concept of virtualization, it means a lot of things to different people. So let me just start off by explaining what I mean by virtualization. Virtualization in general is taking some existing interface, whether it's between two software layers or between software and hardware, and abstracting it in some way. Typically to add some capability that wasn't originally anticipated by that interface. So for example, if you want to multiplex some resources that were originally not meant to be multiplexed, they were originally a single relationship, single consumer, virtualization is often a very logical way to accomplish that. And so in some ways you can think of virtualization as kind of an after-the-fact hack to make something work. And the reason that you do that, as opposed to redesigning the thing, is because there's some value to that interface, usually some backward compatibility that has been built up that you want to retain. So there's some good aspects of that interface, but you want to extend it somehow. So I mentioned resource multiplexing. Resource management is another common reason. So if you want to be able to control, for example, quotas on specific resources, whether it's CPU utilization or bandwidth utilization, oftentimes virtualization makes sense. And then separating things out that were originally combined, putting them in their own isolation boundaries is another common use for virtualization. And you see virtualization all over the place already in computer science and in operating systems. In fact, it's a very common technique, so common that you don't even realize sometimes that it's actually virtualization that you're talking about. So even something as simple as a thread is really a virtualized processor. And virtual memory is a concept that's built into almost every operating system. Sessions is an example of another virtualization concept that's built into the Windows OS. And then, of course, SANs and virtual machines. So that brings me to to the main portion of my talk, which is virtual machines. This slide looks like it was done by a marketing person, and it was. It's the only one in my slide deck that was done by a marketing person, so don't worry. I'm an engineer. I thought I'd throw this up there, though, because it kind of shows that we think of virtualization at Microsoft in a lot of different ways, and there's a lot of different layers that you can virtualize. We provide a client virtualization solution, so for desktops, and that's a virtual PC. In the upper right-hand side, you see virtual server, and we have this new platform that we're developing that will replace virtual server. We also do what we call presentation virtualization, which is abstracting that tight link between the operating system and the presentation layer. This is nothing new. There's been X Windows. We have something called RDP, Remote Desktop Protocol, built into Windows. But it is a form of virtualization. And then in the lower right, we have a set of technologies that virtualizes at the application to OS boundary. And that's really something that allows applications to run independently so they don't conflict with each other. You might think, well, isn't that the job of the operating system? And yeah, it is. That's an example of where we probably didn't do as good a job as we should have with the operating system to begin with, so now we have to put in this after-the-thought solution in order to virtualize the applications. And then at the very center, we have a whole collection of management tools for managing computers, both clients and desktops, that are now learning about virtual machines. So we're teaching our entire management suite about virtual machines because VMs are really proliferating and will become very commonplace. So there's a couple of concepts that I wanted to cover. Many of you are probably already familiar with these, but for those of you who aren't, I'll go over these quickly. At the heart of a virtual machine is this component called a virtual machine monitor, and it's the component that's responsible for maintaining those boundaries between the virtual machines. And there's a couple of different ways you can implement a VMM. There's the whole concept of a hosted VMM, where you're running it effectively on top of an existing operating system. And there are several examples of that I've listed. VMware Workstation is a popular hosted VMM. KVM is a hosted VMM that's now part of the Linux kernel. And Virtual PC and Virtual Server are also examples of that type of VMM. On the other side is a VMM arrangement that's called a hypervisor. And a hypervisor is a VMM that runs really on the hardware. There's no other operating system under the VMM in this case. And all of the operating systems run above it. And there are some classic examples of hypervisor. Hypervisor is an IBM term. I think we have some IBM folks in the audience. A hypervisor comes from the days when IBM referred to operating systems as supervisor programs. And when they wanted to put multiple supervisor programs on a single mainframe, they had to have a supervisor for supervisor programs, hence hypervisor. So it's kind of a term that's become revived now as virtualization has hit the PC market. There are several examples of a hypervisor in the market already. VMware ESX is the most popular one today. And the Zen hypervisor is the open source community. It's their VMM or hypervisor. And then the hypervisor that my team has been working on at Microsoft, we refer to as Windows Server Virtualization. You'll see WSV throughout my talk. You might have also heard it called Viridian, which is the code name that I came up with, and it has made its way to the press. So you might see Viridian in the press a little bit. WSV is part of the Windows platform, so it'll be part of Windows Server, and it is a true hypervisor. It takes advantage of some new processor features that are built into both Intel's and AMD's processors. In fact, it requires these new extensions. So we're making a big bet on the new hardware that's coming out, and it will appear as part of the release that we have recently referred to as Longhorn Server. That was our code name for it, but the marketing folks recently came up with a really snazzy title of Windows Server 2008. That was a big surprise, huh? So what is a hypervisor? Or what were our goals of the hypervisor? So we decided that we wanted to make a very simplified hypervisor. We wanted to strip it down to its essence. And I'll explain why in a little while. But basically what our hypervisor does, it's really a partitioning kernel. So it's an operating system kernel, and it provides isolation boundaries between different what we call partitions. And these are logical partitions or software partitions. They're not hardware enforced. The hypervisor that we wrote is a very thin layer of software. It's well under 100,000 lines of code, which is pretty small for a kernel. Compare that to Linux or the Windows NT kernel, which is the basis for all of Windows systems today. That's very small. We really wanted to make it small so that it's a small trusted computing base. So both for security and reliability reasons. It doesn't contain a built-in driver model, which is an interesting thing. So we wanted to leverage all of the drivers that have already been written for the Windows source code base. We didn't want to create another driver model for everyone to port to. So the drivers get pushed up into one of the partitions or multiple partitions, and then they talk directly to the hardware. And the last bullet point, a lot of people find this really surprising. Our hypervisor is OS agnostic. A lot of people think, well, why don't you make it tied to Windows? The reason, there's a couple of them. First of all, we wanted to make sure that we could run other operating systems as well. Linux is important to our customers. As much as I hate to admit it, it is. So other operating systems that run on x86 PCs and servers, we want to be able to support those in our virtual machines. The other reason is the Windows kernel has existed for going on 12 to 15 years now. And kernels don't have an infinite lifespan. So we anticipate that over time we're going to need to replace our kernel, or at least evolve it in a pretty major way. So we didn't want to build in assumptions about the Windows kernel into our hypervisor, because I want that to have an even longer lifespan. So we're publishing the full interface to our hypervisor, and other operating systems can talk to that interface if they want. So there's a couple of different architectural decisions that we needed to make when we started on this hypervisor. The biggest decision that confronted us from the outset was whether to go with a monolithic hypervisor or a micro hypervisor. This is the same choice that kernel developers have faced for many years. Do you do a monolithic kernel or a microkernel? And there's trade-offs to both of these. Just like there's trade-offs between a hosted VMM and a hypervisor, there's trade-offs between these two models. And I could argue either side of these. And we decided for a variety of reasons that we wanted to go with the micro-hypervisor approach. And the biggest reason is because Microsoft and all of the companies we work with have a very large investment in drivers. That's one of the real strengths of Windows, is that we support so much hardware out there. We didn't want to go back and ask them to rewrite all their drivers for a new driver model or a new environment. All the drivers run fine in Windows today, so we wanted to keep them running in the environment in which they've been tested. So the arrangement on the right really made more sense for us. That's the same approach that the open source community has gone with Zen. It's different, for example, than the approach that VMware uses with their ESX hypervisor. So I've already gone over some of this, but I thought I'd throw up an architectural diagram. You can tell this wasn't done by a marketing person. This is about as fancy as my slides get. So like I mentioned, our hypervisor creates partitions. We have the concept of virtual processors, and you can create as many virtual processors as you'd like and assign them to partitions. And then there's a small, very simple scheduler inside the hypervisor that schedules those virtual processors on the physical cores of the machine. And it's possible to oversubscribe those, so it does multiplexing. Or if you don't oversubscribe it, then you get 100% of a physical core for a virtual processor. And pretty much all the other things that the hypervisor is responsible for are just maintaining these isolation boundaries. Now you'll notice in the diagram that the hypervisor doesn't, it manages the CPU and the RAM, but the arrows go right through the hypervisor to get to the hard drive and the NIC. And that's, the hypervisor, like I mentioned, doesn't have any knowledge of those devices. The only other point that I'll make on this slide is that the hypervisor does expose a very simplified set of calls that are called hypercalls. It's the equivalent of a kernel call. And when I say small, it's a very small subset. I'd say I think we have 40 total, of which really only 5 are commonly used. So compare that to the API set of a modern kernel. It's very small. Most of the interface that we expose with the hypervisor is defined already by the x86 architecture. And so we just want to make sure that we maintain all of the semantics of the x86 architecture, so all of these OSs that were written to run on that architecture just run. So I mentioned that we wanted to keep the hypervisor very thin and lightweight. And we've accomplished that. Like I said, it's well under 100,000 lines of code. I think we're going to come in at about 75,000 lines, which means that it's well under a megabyte on disk. So that's pretty small. You compare that to the core binary of the Windows kernel, which is about 4 megabytes, or if you compare the full set of binaries that make up the Windows core system, which is about 20 megs. Now, that's big compared to other operating systems, but still a 1 meg hypervisor is relatively small. But we don't get that for free. We have to push the complexity out somewhere. And so we did that in the form of a set of components that we call the Virtualization Stack. And this runs inside of a partition, one of those partitions that you saw in the previous architectural diagram that we call the parent partition. And the Virtualization Stack then is able to control one or more child partitions. So there's a relationship, a one-to-n relationship between the Virtualization Stack, or an instance of the Virtualization Stack, and a set of child partitions. And the Virtualization Stack really implements all of the fun, interesting features of the virtual machines. It could, you could have a very stripped-down Virtualization Stack that does very little. Ours happens to do quite a bit. It includes legacy device emulation, so we can run older operating systems that expect certain old devices to be there. It does VM, what I call lifecycle management, which is basically moving VMs from one state to another, starting, stopping, saving. It exposes a set of management APIs for allowing people to start and stop VMs. It can provide paging support. It can provide snapshotting. It can provide live migration of workloads from one machine to the other. So all of these sort of sophisticated features are put up in this higher layer. So here's an architectural diagram. So you can see the hypervisor stays very small down here, and then the parent partition is on the left. And the line represents kernel mode, user mode. So some of the Virtualization Stack is up in user mode, some of it is down in kernel mode. So let me talk a little while about our device virtualization strategy, because for certain virtual machine applications, device virtualization is very critical. Performance of devices, device virtualization is very important. On servers, there's 2 devices in particular that are important. It's disk and networking. And so the approach that we've taken is, actually we've chosen 2 different approaches. I mentioned that we emulate some legacy devices, some older devices, for which a lot of operating systems already have drivers. And so by having those old emulated devices around, we can support a wide variety of operating systems. Unfortunately, that's a slow way of virtualizing. So we've taken another approach and come up with a new architecture for something that we call virtualization service providers. And here's an architectural diagram. In this diagram, once again, you see the parent partition and the child partitions. One of them is obscured over there, but you can imagine that being duplicated n times. The orange boxes, the storage stack on both sides, are already part of the operating system. So we're leveraging big portions of the operating system already. The white boxes are the ones that we've added for virtualization purposes. On the child side, you see this thing called the storage VSC. That stands for Virtualization Service Client. And over here, you see a corresponding piece called a Virtualization Service Provider. And they act kind of like a client and server. And so when a command comes down, a storage command, like read 20 sectors off the disk starting at this location, comes down the storage stack, it gets sent across to the storage VSP, which then sends it down the stack to the actual hardware on the parent partition side. And so this acts as a multiplexer. You have to remember that there's n of these child partitions, so that it's getting messages from multiple partitions. And then we have a component at the very bottom that's running in all the partitions that we refer to as VM bus. And that's simply a transport layer that makes use of some simple message passing mechanisms in the hypervisor, as well as shared memory. So we can get very fast transfer of both those I/O commands and then the data back in response. So here's another concept that we came up with. It's something that it's a term that I invented. We called it enlightenments. So enlightenment is a change to an existing piece of code that previously had no idea about virtualization. And enlightenment is changing that code so that it now knows about virtualization. So it usually takes the form of an if-else statement. If I'm running in a hypervisor on top of a hypervisor, do this. Otherwise, do what I would normally do. And we've taken this approach. You can contrast this approach to the approach that the open source community has taken. They have a technique that they refer to as para-virtualization. You may have heard of that. Para-virtualization generally, it's very similar in concept, but it generally refers to a separate binary. So there's two versions of Linux kernel, one of them that has virtualization, the virtualization code paths compiled into it, and one of them that runs on a physical machine. And we really wanted to take the approach where we only had one binary, and that really helps us out in terms of testing. It helps customers too, because they don't want to have to manage two different variants of the kernel binaries. They want to have one image that they can run on a virtual machine and on physical machines. And so this approach has served us quite well. And what we found is that we only need to modify something like 0.01% of all the code in the kernel in order to enlighten it, in order to get some very good effects. Those effects are mostly performance related. So Windows Vista, which is already shipping, and Windows Server 2008, which will be shipping early next year, are the first enlightened operating systems that Microsoft is shipping. So they know about the presence of a hypervisor. Previous to that, the OSs didn't know that. They just assumed they were running on physical hardware. And then the final piece that I haven't really talked about is virtual machine management. And this is a really critical aspect to making virtual machines really useful, especially in a data center. So we're investing a lot in tools that allow people to very quickly move from a physical machine to a virtual machine, and then intelligently place those workloads anywhere in their data center. So a lot of you have probably used VMs today for software development, if I had to guess. That's probably the most common use on the desktop. And so some of you may have used it for application compatibility also, although that's used more in enterprises, large companies that have old pieces of software that they need to keep running. And if they want to upgrade to a new operating system, we always like them to upgrade to our latest operating system. So this gives them a way to move forward. There are a lot of companies, for example, in Eastern Europe and in South America who are still using OS/2 to run some of their critical line of business applications. Those poor companies. I don't know if you guys have used OS/2. It's a little out of date at this point. We'd really like to get them to move forward to Vista, or even XP for that matter. And so this has allowed them to move over. So app-compat is a common use for VMs today. On the server side, servers have really driven the adoption of virtual machines. And VMware has done a great job in showing people how VMs can really save them a lot of time and money in their data centers. And people have adopted these very, very much. It's still an expanding market. Still a very relatively small fraction of servers are virtualized in the x86 space. But I think everyone is in agreement that that's going to continue to grow over time and will eventually be the common case. That will be the standard. It'll be rare to actually have a server workload running directly on the hardware. So VMs have a lot of advantages, especially on servers. I'll talk a little bit more about what some of those advantages are in a few minutes. But I also want to point out that VMs are not a panacea. They bring with them some pros and cons. And some of the challenges that you experience with VMs are very real, and we need to acknowledge the fact that those exist and either try and mitigate them or find an alternative solution that maybe avoids some of these challenges. Some of those challenges include things like added overhead. There's always some overhead with virtualization. We're always working to lower that overhead to as close to 0% as possible, but practically speaking, we're not there yet. IBM has a lot of history on their mainframes, especially in some very clever ways of lowering that cost. And a lot of that is by putting very specific assists in the hardware. And we're not there yet on the PC world. We're getting there, but it's going to be a while before we get down to something under 5%. There's also added management complexity when you have to deal with multiple OS images. Now, there's also some management savings, but for example, if you're rolling out your applications, like the OS2 example that I gave, if you're rolling that out to 10,000 desktops in your company, now you have to manage 2 operating systems on every desktop. So have we really saved you money? You have to do that analysis and decide if you're an IT administrator, and you have to figure out, was that a good trade-off? On the desktop, there's also added complexity to user interface, because I think most of the people in this room who have used VMs you're technically savvy. You understand that when there's a whole other desktop that comes up on your machine, you know that that's like analogous to a separate computer, and it probably doesn't confuse you. But now put yourself in the shoes of somebody who is a novice computer user and barely understands the workings of the machine. That really blows their mind. They don't understand, well, why is there 2 start menus? It's really too much for a lot of people. And so companies are concerned about using VMs in this case because they have to retrain their employees. So we're always looking for ways that we can improve the user experience in those cases. Here's another interesting one that a lot of people don't think about. It's an architectural issue. If you think about the core responsibility of any kernel, it has to do with resource management, managing the core resources of the machine, whether it's memory, whether it's CPU cycles, whether it's bandwidth to memory, whether it's bandwidth to your I/O devices. And so a modern kernel is largely about resource management. And the best way to do resource management is to have a component that knows about all the available resources and all the resource asks in the system, and then apply a set of policies so it can divvy those up appropriately in an optimal manner. That's an easy concept, but it's actually tough to do. And it makes it even tougher when you have 2 separate resource managers sitting on top of each other, which is effectively what you have when you put a virtualization layer underneath. So we have a scheduler in the Windows kernel already, a CPU scheduler. Now we added another CPU scheduler underneath it. And in theory, they could conflict very badly. They could kind of work against each other. And so finding the right mix there and making them work together, it makes the system more complicated. And so that's a challenge with virtualization. Another concern that we have, or a challenge that we have, has to do with hardware or device virtualization. And device vendors are always coming up with new ways to add new features to their hardware. If you think about the video cards that you have in your machine, if you're a gamer, for example, you buy the latest NVIDIA card because it has DirectX 10 support, or there's some new feature that you want to take advantage of. The same is true for almost any hardware. If you look at NICs, for example, either 1 gigabit or 10 gigabit NICs, there's always new features like offload features where they're taking pieces of the TCP/IP stack and putting it in hardware. That's how the hardware vendors make their money. They innovate in those ways and they expose these new features. The problem is virtualization is all about abstracting that, and it basically gives you the least common denominator for all the features. And so virtualization is a mixed bag for these hardware developers. A lot of the hardware developers that I talk to aren't really sure they like virtualization. They're trying to figure out how they can make money with it, but this is a bitter pill for them to swallow. Now, virtualizing at the virtual machine layer is not the only solution. There are a lot of different ways that we can virtualize, and there are alternatives to virtualization as well. So I've listed a couple of them here. One of them is virtualizing at a higher layer in the software stack. So for example, SoftGrid is the solution that we have. That's the application virtualization layer that I alluded to earlier. And presentation virtualization is another way that you can do that. So for example, you could run your workload in one place and remote it to another place. And then another one that we're always asking ourselves, since we have access to the Windows kernel and the source code for Windows, we have to ask ourselves, could we solve this problem better by just fixing the root problem in the operating system itself? And a lot of times the answer is yeah, we probably should. We shouldn't use virtualization as the crutch or the hack to work around that really core problem in the operating system. And I'll talk about that a little bit more in a few slides, because there are a few areas that I think that we need to do a better job at Microsoft at fixing some of those core problems in the operating system. And we are making those investments. Some of them are pretty heavy lifting, though, so it's going to take a while. Here's some additional emerging uses for VMs. Some of these are already in the marketplace. VMware has solutions in a number of these spaces. But there's some interesting areas that are coming up, and I think these are probably what I refer to as good uses for virtual machines. And I differentiate between good uses and not so good uses based on whether I think that the problem really should be solved somewhere else or whether it should be solved using virtual machines. VMware, by the way, tends to look at all problems through the lens of virtual machines. And it's not surprising. That's their business. If I were in their shoes, I'd do exactly the same thing. But in some sense, it's kind of like if you have a hammer, every problem looks like a nail. So at Microsoft, we have a lot of different tools in our toolbox, and so we tend to look at problems a little bit more broadly. And we have that option. So that's what we try to do. We try to look at each problem separately and say, well, what's the right way to solve that problem? So anyway, here's some areas where I think that virtual machines really do make sense. So partitioning very large machines. And very large machines today are the very high-end, expensive servers that have 64 cores or 128 threads of execution. You're talking about a $250,000 machine. Not many of those out there today. So that's not a very big market today. But the thing is, with multi-core coming out, with machines, with single socket, with single processors that have 8 cores per socket coming up in just a couple of years, you put 8 of those cores on a motherboard, or 8 of those sockets on a motherboard, and you have a 64-core system very quickly. And those systems are not going to cost $250,000. That's going to come down into the commodity market range, server range. And so we're looking for ways to carve that up and really utilize those resources. There aren't a lot of workloads that you can put on a 64-core system and have it just scale up to that many processors. Windows today, in fact, if you run Windows Server 2008, it won't use more than 64 cores. That's all that the kernel knows how to schedule. We're working on breaking through that limit right now. Part of my team is back in Redmond right now, working on expanding that beyond that limit to 256 processors for the next version of Windows. So we're working right now on the next version of Windows, which is codenamed Windows 7. And that's one of the features that we're working on. But in a lot of cases, there aren't a lot of workloads that can take advantage of that anyway. Databases are kind of the only one that really do today. So in a lot of cases, you really do want to break up the server into smaller chunks and run workloads in those partitions. Client consolidation is another emerging area. We already have a solution in this space called Terminal Server, which allows people to run a whole bunch of instances of a client operating system, Vista or the equivalent, on a server, and then just remote it to a thin client or to a desktop. And that works pretty well, but there are some cases where it doesn't work so well. There are some cases where there's resource management leakage between the different sessions. Sessions are the isolation boundary that we use. And so virtual machines offer an alternative approach to this problem. And so I think that that's probably going to become very popular in the next several years. It's already getting some uptake. Server appliances is another area that I think virtual machines will continue to be used. A server appliance is basically a pre-configured server workload. So you get this thing in a prepackaged form, you throw it on a host machine, a physical machine, and you get it started up with almost no configuration. Maybe answer 1 or 2 questions and you're up and running. And these can be anything from routers to firewalls. It's usually a single purpose fixed function device. And they're especially important for situations where you don't have a dedicated IT staff. So you don't want to have a lot of configuration. And then finally, I have security on here. We have an issue. We're always fighting the security battle. We've done a lot of investments inside of Microsoft and inside of the Windows kernel in particular to improve our ability to prevent security attacks and then to be resilient in the face of a vulnerability. One of the things that we've seen emerge over the last couple of years is kernel malware. I think there was a previous talk about this. I wasn't able to attend, but using a hypervisor at the more privileged layer. The way that the hypervisor works, by the way, is it runs at a more privileged layer than the ring 0 layer that the kernel runs in. You can think of it as ring -1 almost. We think of it that way sometimes. So if you have something running in ring -1, it'd be really bad if it was the malware running in ring -1. But if you have ways to keep the malware out of ring -1, so for example, our hypervisor doesn't allow any third-party code to load. It doesn't have a driver model. So it's much easier for us to keep the malware out of ring -1 than it is out of ring 0. Ring 0, we're running the kernel and we load third-party drivers into that environment. And so it's more difficult for us to keep the malware out of there. And so by having a layer underneath, we can help the kernel protect itself effectively. We can give it a fighting chance in that arms race. So I mentioned that some of the existing limitations in the operating system are driving some of the interest in using virtual machines. And these are some areas where I think we need to do a better job at Microsoft. And some of these also apply to other operating systems, by the way. They're not necessarily unique to Windows, although I think Windows is especially bad in some of these areas. But these are some of the things that are driving the use of virtual machines. And I'll go through each one of these. The biggest one, in my opinion, is the lack of state separation. This is a problem that we've faced in the Windows OS. We have this concept or this thing called a registry, which a lot of you probably know about. It's this pile of stuff, and it's a single resource, single repository that contains everything from OS settings to application settings to user settings, and they're all in this one big ball. And that makes it really tough to do things like upgrade your operating system. If those were nice and separate, you should be able to slip out the operating system with its associated settings and slip a new one in and not have to reinstall any of your applications. It should be really easy. For those of you who have gone through an upgrade process, we do try to upgrade operating systems. So if you have XP running on your machine and you buy a copy of Vista, you can go through an upgrade process, but there's a lot of stuff that goes on under the covers. We actually install a whole new copy of the OS and try and pull over pieces. We kind of rummage through all that state and pull over the pieces that are appropriate. And it works some of the time. So it's not pretty today. So we're working on fixing some of these things, but this is something that's going to take quite a while, and we're going to potentially break some application compatibility in the meantime. So maybe we can use VMs to fix the application compatibility in the meantime while we fix the root problem in Windows. And I mentioned this one a little bit before in the context of application virtualization, but there's still a lot of software conflicts that occur where there's 2 versions of the same DLL or 2 versions of the same application or incompatibilities between one application and another. Maybe they both install the same COM interface, the same scripting interface. and there's conflicts between the two. So these happen more often than they really should. And so we're looking at ways that we can fix that in the operating system by providing a fully deterministic application model and extensibility model. The fact that there are uninstaller programs that are sold for Windows, and these are consistently top-selling programs, is very embarrassing. You shouldn't need an uninstaller program of any sort. The operating system really should do that for you. So that's another thing that we're focusing on. And resource management. I mentioned this is one of the main jobs of a kernel, is managing the resources in the machine. And our kernel does an okay job, I think, but it could do a lot better job. And there are places where it is not doing a good enough job right now. So, for example, providing more controls around workloads, utilization, memory usage, I/O bandwidth, being able to control those, put limits on them, measure them, so provide metering of those resources. We need to do more in those areas. So we're going to be investing more. Wrapping them in a VM in the meantime is an okay solution, because we can provide those at the VM boundary layer, but really we should provide that in the operating system. And then application compatibility. This one comes back to bite us all the time. Customers really want us to maintain that application compatibility from one version of Windows to the next. I'm sure you've experienced this before, where you try a new version of Windows and some application that you used to run no longer works, or there's some behavior that's not quite right. I've experienced that too, and it's very frustrating. And yet, that's a real challenge for us, because a lot of the applications out there make assumptions that maybe they shouldn't be making. And in those cases, we can't really move the operating system forward without breaking them. So now we have this choice. Do we move it forward? Do we fix that security hole? Do we add that new feature? Or is AppCompat going to say, no, we can't do that? It's too important to keep that application running. So virtual machines are one way we can handle that. But virtual machines are also a little bit, it's kind of a sledgehammer approach to solving that problem. So just to wrap up my talk, the virtualization is a powerful tool. I might sound like I'm a little bit negative on virtualization toward the end of this talk, but I want to let you know that I spent most of my career working on virtual machines and virtualization. So I really enjoy the topic, and it is a very powerful tool, and people are getting a lot of mileage out of it. But I also don't want to abuse it and use it in places where it shouldn't be used. So I'm trying to look at things holistically when I look at which problems we should solve using virtualization, which ones should be solved using other techniques. So let me move on. I have a couple of demos here, and they use Virtual PC, which some of you may have used in the past. This isn't really a great demo of what people are actually using virtual machines for, but it's still fun. So I'm going to show it to you. I call these stupid virtual PC tricks. So I mentioned that we're working right now on this thing called Windows 7. That's the code name for it, by the way. Some really creative person came up with the code name, Windows 7. Does anyone know why it's Windows 7? Well, Vista was number 6. And number 5 was XP. And number 4 was NT4. Number 3, you have to go back to a previous kernel. Some of you are probably even too young to remember Windows 3, Windows 3.1, 3.5. Yeah, 3.5 was the first NT version of the kernel, the first modern kernel that was incorporated in Windows. This is Windows NT4, which some of you might remember. And it's running in a virtual machine. And you can see it has some of the same feel of today's operating system, but it's running in a virtual machine. And for those of you who have used products, Virtual PC or VMware or other similar products, you know that you can very quickly save the state of a virtual machine to disk and reload it back from the point where it stopped. So that's a pretty cool trick. So this is Windows 3.1.1, which some of you may remember, probably not fondly. It happens to have an application installed on it that some of you may have heard of. It wants me to make a backup. So that was not necessarily Microsoft's proudest moment there. But Windows 3 was really the third rev of Windows. And a lot of people don't realize that. There were actually 2 versions of Windows before that were not big successes. It takes a while to change a paradigm or to get people onto a new platform. And so I actually have Windows 2 here. Now, that was the BIOS booting. You can see how fast it booted. That's Windows 2. And you can see it came with some nice little utilities like calculator. Oops. So there's the calculator functionality. We can start Notepad, Paint. Looks just like Photoshop, huh? So that was Windows 2. I actually have Windows 1 here also. This one, you can watch how fast this one boots. So nice and fast. This one is hard to navigate in because it doesn't know about arrow keys. Arrow keys weren't on the keyboards at the time. It also doesn't know about mice. So you basically have to type select. So like I'll hit P to get to Paint. So there's the... So that was Windows 1.0. So let me fast forward to the future, and I'll show you something that we did recently. This is the core of Windows 7. This is a collection of components that we've taken out. A lot of people think of Windows as this really large, bloated operating system, and that's maybe a fair characterization, I have to admit. It is large. It contains a lot of stuff in it. But at its core, the kernel and the components that make up the very core of the operating system actually is pretty streamlined. It's still bigger than I'd like it to be, but we've taken a shot recently at really stripping out all of the layers above and making sure that we had a clean architectural layer there. And we created what we call MinWin. Now, this is an internal only. You won't see us productizing this, but you could imagine this being used as the basis for products in the future. This is the Windows 7 source code base, and it's about 25 megs on disk. You compare that to the 4 gigs on disk that the full Windows Vista takes up. We don't have a graphics subsystem other than text in this particular build. So you can see that's our Windows flag. This is running in 40 megs of memory. So, you know, a lot less than your 2 gig machine that you're used to. And what it has is a very simple HTTP server running inside of it. So if this works, I should be able to talk to it. And so you can see the HTTP server is not very full-featured. It's designed to just spit out the task list. And you can see there's a very small number of tasks running on there. There's a total list of the files that make up the system. There's about 100 files total. Compare that to about the 5,000 files that make up all of Windows. And then here's the memory statistics. So I have it configured to run with just under 40 megs of memory, and there's 7 megs free. So that's kind of proof that there is actually a pretty nice little core inside of Windows. Yeah, question? Yeah, the question is MinWin a good way to run web servers? You'd need a lot more than MinWin to run a full-featured web server. You know, most web servers today serve up dynamic content. You need a lot more than this. We are starting on this path at multiple layers of the system. So Windows Server 2008 is based on this thing called Windows Server Core. And it basically ships in this minimal state. And when I say minimal, it's about 1.5 gigs on disk. which is still a lot bigger than what we're talking about with MinWin. But it has all the stuff necessary to run the different server workloads. And so then you can install a web server, or you can install the virtualization role, or you can install the database role. And then it adds just the components necessary for that role. And so it keeps the footprint down. I mentioned 1.5 GB on disk. That's still pretty big. In memory, it's much smaller. So that contains all the drivers, and many of which you don't need for any given platform. So yeah, we're going down that approach, but it'll be a while before you could build something directly on top of this really tiny core. Like I said, we don't have any productization plans. It's more of an internal. Like I said, we don't have any productization plans for it. We're definitely going to be using this internally to build all of the products that are based on Windows. We build a lot of products based on this kernel. It's not just the operating system that's running on many of the laptops in the room. It's also the OS that we use for Media Center, that's running in a lot of people's living rooms. It's used for servers. It's used for smaller embedded devices. It's used in a lot of different ways. And this will provide us the ability to move into even more areas. Yeah. Yeah. Let's open it up for questions. I'm done with my presentation. So the question is, if we were to design the kernel from scratch and could assume that there was a hypervisor underneath, what would we take out of the Windows kernel? I'm not sure we'd take anything out. I think that we would probably want to have the option of running just a very stripped-down kernel on top of raw hardware. In cases where there's the necessary hardware support for a hypervisor, like the x86 now has, this laptop, for example, has support for our hypervisor, and a lot of the laptops you have, if you bought them in the last year, probably have that as well. But, for example, you won't necessarily find it in low-power ARM cores today. And if we want to be able to take the kernel that we write and keep it portable, we probably don't want to tie it to a hypervisor necessarily. Yeah, if you start to really intermix the two, then there are some disadvantages to that. Like I mentioned, if you want to keep our kernel such that we can run it either on a hypervisor or on bare metal where that makes sense, then it doesn't really make sense to have those tight tendrils between the two. Yeah, you do get some redundancy, but with the approach that we've taken with our hypervisor, we try to strip almost all of it out. It has a scheduler and it has page mapping, but that's about all that you'd see as redundant. And so if you use it as just a partitioning mechanism, even the scheduler at that point becomes very simple because it's just mapping virtual processors to physical cores in a one-to-one fashion. There's almost no policy in the scheduler at that point. Sure.
You were talking about using I/O mapping, kind of. Is the way that using this Viridian that you've been talking about, is the graphics support going to be able to talk directly to graphics cards, or will they still be like running in a separate process in the parent OS?
We haven't spent a lot of time working on graphics because we focus mostly on servers for now, and servers, graphics aren't that important. So the answer to your question would depend on what usage scenario we're really targeting. And if it's a usage scenario where we need to be able to multiplex different virtual machines on a single GPU, for example, a single piece of video hardware, that's a very different requirement than if you have, say, an application compatibility scenario where you have the older operating systems probably don't need that high-end video capability anyway. They probably just need a very simple frame buffer. So it really depends on the requirements and which solution you're talking about. And we have some ideas for doing either of those. There are some interesting things that the hardware vendors are doing to enable the multiplexing one, the first one that I mentioned. So you could imagine the GPU vendors providing ways of effectively partitioning their hardware between virtual machines. We're seeing that both in graphics and with NICs now, where the hardware will actually have some of the traditional multiplexing built into it that has traditionally been up in the driver area. If you think about the main purpose of a traditional driver is to accept I/O commands from multiple sources, multiple clients, whether they're processes or queues, and then figure out how to order them and send them to the hardware. It's an arbiter. And so some of that functionality now is moving down into the hardware as the transistor budgets continue to go up. And so, like I mentioned with the GPU, you could imagine the GPU knowing about multiple contexts. That's already being done today without the context of virtual machines, because in Windows Vista, for example, we take advantage of 3D much more than we have in previous versions of Windows. In previous versions of Windows, the GPU was really thought of as this a single resource that one process could use. So when you'd launch a game on Windows, it would take over the whole screen, and nothing else could use the GPU at that time. Whereas in Vista, we have a new graphics engine that allows multiple processes to share the GPU, and so the GPUs are getting smarter about knowing about different contexts. So you could imagine that same sort of functionality being used to separate the context to different VMs.
So x86 hardware extensions for virtualization aren't a complete solution for virtualizing the x86, and nor are they always the best performance choice. For Viridian, have you considered any techniques such as binary translation to compete with VMware? And also, what techniques and what additions would you like Intel and AMD to add to VTX and SVM in the future?
Okay. So have we considered things like binary translation? Well, binary translation is something we use in virtual PC and virtual server today. So I'm very familiar with that. That's one of my areas of specialty. Virtual PC, by the way, started off as a Macintosh product, for those of you who want to go way back in time. And their binary translation was the only option, because you're talking about, at the time, it was PowerPC in the physical hardware and x86 software in the virtual machine. So everything needed to be translated. We don't sell that product anymore, but the binary translation engine that I wrote for it is still shipping in another Microsoft product. Anyone want to guess what it is? It's the Xbox 360. If you think about it, the first Xbox was based on x86. Xbox 360 is based on PowerPC. And so if you want to run Halo 1 or 2 on your Xbox 360, it goes through the binary translation engine that I wrote, which is pretty cool. So anyway, we definitely know a lot about binary translation, and we've leveraged it in the past, but we've moved away from it for Viridian. And the way that we've done that is we've worked closely with Intel and AMD and made sure that they got in enough that we weren't going to suffer major performance bottlenecks. And then in the areas where we weren't able to get the things added, we've modified the operating system. And so those are the enlightenments that I alluded to before. So with that combination, we're going to do fine on performance. There's more we can do, and we're always working with AMD and Intel. I'm not at liberty to talk about things that they haven't announced yet, but some of the things that they have, that we've worked on them with, they have announced. I think that Intel recently announced some things. You've probably heard of NPT and EPT. nested page tables and extended page tables or enhanced page tables. EPT is Intel's and NPT is AMD's. Both of them are very similar in concept, but they basically allow us to virtualize the memory management unit without nearly as much overhead. EPT is also my initials, so I tend to prefer that one.
You said that the VM doesn't know anything about the hard disk. Wouldn't that cause locking problems?
Can you repeat the question? I didn't quite understand what you meant.
Your virtual machine infrastructure, it didn't see your diagram showed it didn't know about hard disk, so it was talking directly to hard disk, right?
The hypervisor doesn't.
The hypervisor, yes.
The virtual machine, the virtualization stack does know about the hard drive. And so it, for example, we provide a couple of ways of providing storage virtualization. One very common way is to use an encapsulated file format that we call a virtual hard drive, or a VHD file. And that's sitting on the hard drive of the parent partition. And it's usually just sitting in a file system that's mounted by the parent partition. And so if I can go back to the slides. When the command comes down from the storage VSP and goes down the storage stack, it actually goes through the file system on that side. Now, we also have another mode where you can have it just directly write to a LUN or to an entire partition on a hard drive. But most people actually use it with these encapsulated files, these VHD files.
How do you think companies will react to Microsoft version of hypervisor, considering that it's kind of like a single point of failure, and you guys have like a not very good reputation with Windows in particular, crashing all the time. If I have a $250,000 computer and I have a hypervisor and it crashes, it will crash all my partitions. What do you think about that?
Well, that's one of the reasons that we really wanted to make sure that the hypervisor, which is the largest new piece of code that we're adding to the system, is as simple as possible. Simplification is really the answer to reliability, in my opinion. This is the organization that we have here does have a single point of failure in the sense that the parent partition has to run an operating system. And that's running a copy of this Windows Server Core that I mentioned. It's this stripped-down version of Windows that's still rather large. In terms of single point of failure, the core of Windows itself is pretty solid. And we know this because we get direct feedback. We have these feedback loops. Anytime you actually see this, if you're a Windows user on your desktop in the form of a dialog box. If you've ever seen a blue screen, and hopefully those you haven't seen many of them recently, we try to get rid of those, and I think we've been doing a better and better job over time. But if you do happen to experience a blue screen, normally what happens is it reboots and then it comes up and says, would you like to send this to Microsoft? That's our feedback loop. And we use that to expunge the operating system bugs and the driver bugs out of the system. And so we have a lot of numerical analysis that goes into figuring out where those problems are. And so we have a very good idea of exactly how reliable our core OS is and how reliable the various drivers are that our partners ship. And Windows itself is, the core of it is actually very reliable at this point. So I don't think customers need to worry about Windows being the single point of failure. In a lot of cases, the hardware itself on these servers is less reliable than the actual software. On really high-end servers, that's not so much the case. They put a lot of redundancy in the hardware also. But in commodity servers, the hardware is actually accounting for a larger percentage of the failures.
So in the security section, you mentioned about dealing with kernel malware, such as the hypervisor rootkit. How would you deal with another set of security problems, such as breaking out of the VM and basically having the host compromised, in the sense that you would basically, the attacker would essentially have control of the hypervisor by basically hyperjacking one of the VMs?
Yeah, so that's a great question. How do we know that our isolation boundary is secure? How do we know that somebody running in the child partition can't break out and either impact another child or the parent partition? We worry about that a lot. We do a lot of work to make sure that we've analyzed the system. We do very sophisticated penetration testing. I've hired several outside firms to code review everything in the hypervisor, to do design reviews of everything. We've worked with some of the three-letter agencies, both in the US and in Europe, some of the security community. They've looked at our design and our code. So you can never be sure that it's 100% solid, but we're putting a lot of work into making sure that we don't have those sort of problems. Virtual Server has been in the market for about 4 years now, and we found one bug so far, and we very quickly patched that one. So if you know of any, if you suspect any, let us know. We'd love to hear. But we think we've done a pretty thorough job of trying to of making sure that no such holes exist. All right, I think we have to wrap up now. Thank you. I can take additional questions offline if you have any.